Thank you for joining us today for our webinar on using synthetic data to improve accuracy of scalable machine vision in manufacturing. Okay, so I am Chris Sanders. I am the COO and head of product of Rendered.ai. I am responsible for marketing, product management, and a variety of other things at Rendered. We're a seed stage startup. My background is about 25 years in software development as a developer and consultant. And then I also spent about 15 years in product management. And you can contact me at chris@rendered.ai. Josh, would you like to introduce yourself?
Yeah, so welcome everyone. So I'm Josh Pickard from Eigen Innovations. I'm the director of innovation at the company. So that has me focusing on a lot of the technologies and sensors and different things that we deploy and build in order to power machine vision within manufacturing. I lead the R&D team at the company, which is located in Fredericton, New Brunswick in Canada. And you can reach me at the contact information below if you have any questions.
Awesome. Well, thank you, Josh, for joining me today. We are excited to be able to collaborate with Eigen and Josh to put on this webinar. And again, we're going to focus today on improving scalable machine vision in manufacturing. What I'm going to focus on first a little bit is an intro and overview of Rendered.ai and what we're all about. We're going to give Josh plenty of time to talk about Eigen Innovations and their work in using synthetic data in machine vision. And then we'll wrap up with some Q&A. What we would ask is during the seminar, if you would please type your questions into the webinar Q&A window that's represented by the couple little question bubbles. And we will both verbally and we can also in text answer questions after the presentation is over. We're going to shoot for about 30-ish minutes in content, maybe less if we go too fast, and then we'll save plenty of time for Q&A. Rendered.ai is a seed stage startup based in Seattle. We offer a cloud-hosted platform in AWS that enables customers to generate simulated synthetic computer vision content, imagery, video, and other content to help overcome the challenges in acquiring and using real sensor data. And I'll explain a little bit more about that in a sec. If we look around what's happening today in the market, and in just about every market, from manufacturing to warehousing, logistics, medical, healthcare, insurance, everything around us is being instrumented, from the light bulbs over your head to your phone to thousands of new satellite sensors being put up in the sky. That centralization of everything is leading to a massive tidal wave of data that is approaching us. Typically, what we talk about, the tool that we expect to use and apply today to process all of that data is artificial intelligence, sometimes also called machine learning systems. In other domains, could be called computer vision or referred to as machine vision. And what we see is that there are some typical barriers that limit the adoption or deployment of artificial intelligence. We find that often there is excessive cost and time required in purchasing and labeling real sensor data. So if you need to pick out every person or every car or every object in an image, that takes time. We also find that if you're relying on training algorithms based upon real sensor data, that you only can capture what happens in reality, and often the distribution of events that you're interested in, such as defects or identifying missing parts or equipment, those things often are rare, and so it can actually be hard to capture enough data to train AI without bias. In many cases, customers want to try to deploy a system in place that is going to use artificial intelligence to process data, but they want some surety that this is going to work before they go through expensive deployment or implementation. So you need data to train your algorithm, and without the data, it's impossible to innovate and move forward in some cases. And finally, what we find is data labeling is imprecise and incomplete. I believe that Eigen in some cases uses thermal imaging. We have customers that use synthetic aperture radar and X-ray. And what we find is that humans aren't really that great at identifying things in alternative sensor modalities such as X-ray, multispectral, and hyperspectral imaging. Another issue that it ends up that our customers end up encountering is that they may think that they're training an algorithm to solve a particular problem today, but yet we know that that problem is going to change next year. So that the rare objects or the defects or the parts that they're looking for in their computer vision imagery are not going to stay the same forever. Business is changing faster and faster than ever today, and we know that the problems that we're going to be trying to address and optimize next year will be different from the problems we're addressing this year. Back to the sensorization of everything, what we also are seeing is that the vast majority of data out there is unstructured, unlabeled, and not ready for AI. And so what we see is that there are tremendous issues when using real data to train algorithms to make decisions and make business optimizations. And what we find is that synthetic data or engineered data that AI can actually interpret as real data has the potential to help solve this AI data problem. Synthetic data is designed to attempt to address specific algorithm training processes. If you need rare objects, you should be able to design a data set that has those rare objects. If you need greater variety in defects or smudges or misordered parts, you should be able to actually generate synthetic data that represents those things without having to actually go and simulate all those things, replicate all those situations in the real world. So what we see is that traditionally a lot of customers, especially computer vision scientists, engineers, they end up being stuck with whatever data they're given. They do some training, they kind of do some validation, and then they get what they get. With synthetic data, what we see is that tomorrow's workflow for AI actually incorporates a different workflow in which a data scientist, computer vision engineer can actually design and create the data set that they think will solve their problem, train algorithms, test, and then compare the results. And if they need to, they can actually update the creation or generation of synthetic data to go back in and see if they can improve on that training. Synthetic data is computer generated, so it tends to be inexpensive. You can generate lots of it. It's generated with 100% accurate labels. You can still use real data sets for comparison and post-processing. And then data can be designed for edge or impossible cases, and specifically for removing bias in diverse cases, such as trying to train for very rare defects, or even trying to remove bias in skin tone in human images. Rendered.ai offers a platform as a service that enables our customers to build and design the simulated content that they need without having to worry about the cost of setting up and maintaining cloud infrastructure to generate lots and lots of data at scale. Rendered includes collaboration capabilities, data set management, a developer framework for building out simulations, wrapping simulations. Rendered's platform allows you to include a variety of third-party content and simulation capability. And as you can see, on top of the platform, what we end up helping our customers build, or sometimes our customers build themselves, are vertically oriented, what we call synthetic data channels that are designed to output data to address specific needs. We have diverse customer cases that range from vehicle interior ground-based cameras for things like security and object detection use cases. We are experts in physically accurate synthetic data, and we have access to some simulation capability from a variety of third parties, including some academic institutions for things as complex as X-ray, physically accurate X-ray and synthetic aperture radar. And our system is actually deployed as part of AI pipelines in several customer cases, such that our customers can actually headlessly configure and drive synthetic data generation and then export or import data from Rendered.ai for use in their own automated training pipeline. Okay, and so a few months ago, about a year ago, we joined a networking company, corporate group called AI Partnerships, and I came across a company called Eigen Innovations, and it actually is quite possible, I don't recall now, Josh may have reached out to me, but we got on the phone and we saw obvious opportunity to work together, and so I'm super happy to be able to host Eigen today. Eigen, for us, was one of the proof points that synthetic data really can work out there in the field. And so now I'd like to give Josh the opportunity to talk about how they are using synthetic data and how they explored Rendered.ai as an option for increasing some variability in some of the training that they're doing. Josh, you want to go ahead and take it away?
Yeah, thanks, Chris. So I'm excited to be here to talk about Eigen's approach to scalable machine vision in manufacturing and the relationship that we had with Rendered.ai to explore synthetic data for further improving the accuracy of the models that we actually deploy. Do you want to go to the next one, Chris? So who is Eigen Innovations? So Eigen is a Canadian-based company founded in 2012 that helps manufacturers from all industries unlock the full potential of machine vision within their application. So at Eigen, we provide scalable end-to-end software products to allow customers to do everything from digitally designing their machine vision system to what we do with software in order to process image data. And actually deploy machine vision systems that leverage machine learning. Our unique offering combines both cloud and edge-based software in order to have real-time quality inspections that we can control and manage through very simplified interfaces. Our manufacturing end users vary quite a bit, both in discrete and continuous manufacturing applications. To date, we've targeted automotive and plastic manufacturers, all the way to medical device manufacturers, deploying software such as thermal cameras and color cameras and collecting process data in order to solve very complicated manufacturing quality inspection problems. At Eigen, our focus is to provide our customers with machine vision solutions that scale. So we want to work with our customers in order to build out a solution that works, and then be able to take that solution and scale it across their enterprise. And we've done this with many customers to date. So we help customers solve very complex manufacturing problems, and then scale these from one line to many lines, even to many factories. To date, we've deployed solutions all across the globe and process massive amounts of data in real time to generate quality alerts and actions. And you can see the scale of the data that we collect and process on a daily workflow, such as 600 million images that we process from all of the deployed cameras in order to make these real-time predictions. Next slide. So what are the main industry-wide challenges that currently limit successful machine learning solutions within manufacturing? And there are a few. We'll focus on the three main ones here. The first one is around data requirements. In order to have a successful machine learning solution, it requires large data sets that are properly annotated, that have enough coverage of the types of defects or features that you're looking for so that the model can be robust and perform well enough for the application. These data sets are often deployment specific, meaning that when you move to a new deployment or a new line, you often have to repeat this data set collection and annotation, which adds just to the scale, the severity of generating these data sets throughout the enterprise. Moving on to model development and management, this can be very complex. The deployment-specific models that are often generated quickly become a nightmare to manage and develop, and just refine on an ongoing basis. Also, these development-specific models or deployment-specific models often require custom augmentation strategies in order to get better coverage of the types of features that you want to inspect. And lastly, even when you have a solution that is working on the first machine, often scaling that to additional machines, additional deployments, can be difficult and even impossible because of comparability of the data sets over these machines. And lastly, for scalability, if you have to change your hardware, for example, a new sensor, a new lens, change the placement of the camera, the data set changes completely. And that means that the model performance can be severely impacted. You can go on, Chris. So what is our approach? And for us, image standardization is a key component to building a machine learning model that scales and works well within manufacturing. And so I'll take the opportunity to define what we mean by image standardization. So this is the concept of eliminating undesired variations from image data while ensuring that we retain desired variations in the resulting data. By removing variations, this means that the model that is trained on these images only needs to learn the right features for the task. So things such as background, perspective variations, we can completely remove that from the data so the model doesn't have to learn it. The key benefits of image standardization include significantly smaller data sets. Compared to raw data, similar performance can be achieved with a model with substantially smaller data sets. It also means that we can take a model trained on this data and scale it to a new machine without actually introducing new data in some cases. On the model development side, rather than deployment-specific models, we can actually change to a single model that covers all deployments because the data sets of all of these deployments are compatible and standardized. And this means reductions in model tuning time and decreased effort to actually manage this model throughout the enterprise. And on scalability, so image standardization is actually a camera agnostic technique. It means that we transform the image from a raw camera associated with hardware into a representation that doesn't have a relationship to the physical aspects of that camera. And what this means is that we can actually use different cameras across different deployments with the same model without impacting scalability, which makes it much easier to scale a solution when image standardization is used. You can go on, Chris. So I'm excited to announce our newest product offering called Eigen Image Twin. So Eigen Image Twin is something that's been in the works for over 5 years, and we've been using it internally and deploying it to customers throughout that time. It allows us to improve the performance and scalability of our solutions. And basically, Eigen Image Twin is application agnostic software that applies a CAD-based image standardization technique and allows us to generate standardized images that allow the development of highly scalable and high-performing machine learning models. So how does the technology work? Quite simply, we take a raw image, such as a thermal image we see here. We combine that with CAD of the part, and we pass that into Image Twin, which performs a bunch of operations, including object pose estimation, texture mapping, computing visibilities, in order to generate an internal 3D representation of every part that we inspect. This internal representation can get rendered from a fixed perspective in order to generate these standardized images that you see to the right. And so we can generate these standardized images for any raw image input. And we do this real time in factories today. You want to go to the next, Chris? So the software supports all kinds of different image formats and is deployable both on cloud and edge use cases, depending on the application. The other thing to note about Eigen Image Twin is that it's not just for single camera inspections. It can also be leveraged for multiple camera inspections, where we can take multiple images as an input, fuse them together through Eigen Image Twin in order to generate that one standardized representation as an output. And so today, the majority of our machine vision deployments that we use for discrete component inspection actually leverages Eigen Image Twin technology to ensure that we generate scalable solutions for our customers. The next one, Chris. And so I'm also excited to announce that we've taken our internal tool sets and productized them. So the technology that we've developed over the last 5 years for image standardization is now available to the public to use and explore. So Eigen Image Twin is now available for free beta access. You can access, enroll for access at Eigen.io today. And we're very excited to see what the public can start to do with this tool set. It's provided a lot of benefit for us within manufacturing in order to scale solutions. And we know there's all kinds of interesting things that people will do with this tool set going forward. So please feel free to sign up for Eigen Image Twin. And we look forward to seeing what kind of problems people can solve. So now moving on to the second part of the talk. So the synthetic data investigation that we've done using Eigen Image Twin combined with the synthetic data toolsets provided by Rendered.ai. So it's important to note before we dive in the difference between undesired versus desired variations. It's a key concept in achieving good results with synthetic data. So as I showed, Eigen Image Twin removes undesired variations from the data set. But what remains is a data set that has desired variations within it. But sometimes the data set remaining still has insufficient coverage of these desired variations that we expect and that we require. So synthetic data is the key approach to introducing additional desired variations that can help us improve the performance of these models. So the application that we targeted for this investigation was surface inspection of defects on high gloss painted parts. In order to generate this data, we use the Eigen deflectometry inspection system that you can see to the right. And this uses a technique of synchronized lighting and image capture combined with specialized processing in order to amplify the visibility of defects, such as scratch and dirt and contamination. And then we train AI models in order to detect these service defects in real time as these parts are being manufactured. So the first part of the investigation is the collection of our raw data set. So in order to do this, for this investigation, we produced a variety of different parts, had them professionally painted, and defects imposed that consist of dirt and scratches randomly placed on the surfaces. And then we had to annotate thoroughly each of these images. So there were 221 raw images that we generated for this data set. Each of those was annotated, and this formed our raw data set. So having this raw data set is great, and that allows us to build models, conventional models based on raw data. But we know that standardized data can significantly improve the performance. So the next step of the investigation was to generate standardized data using Eigen Innovations, combined with the part CAD of the part that was being manufactured. So you can see what these standardized images look like for this part in the top two images. This allows us to remove undesired variations, including background variations and perspective variations, so that the data generated is highly consistent, ensuring that the model will be able to perform better by focusing on the right features. So we took each of the raw images and we generated a corresponding standardized image from that, and that gave us our standardized data set. So the other interesting and quite beneficial aspect of Eigen Image Twin is that internally it has a representation of a 3D asset of every part that goes through it. So for the purposes of this investigation, we built out a custom pipeline to extract that 3D asset and turn it into a Rendered.ai compatible Blender file that we can take and insert into their pipelines. And so you can see what these 3D assets look like. The Blender file, we created customized shaders in order to allow us to accurately display and render the image data on that 3D asset. And also different layers for the different defects that we annotated, so that through the Rendered.ai software, we can actually get out each defect annotated within the synthetic data that is produced. So those Blender files were generated for each image, each raw image, synthetic image that we had in our data set. So we used each of those Blender files within Rendered.ai's synthetic data generation software in order to generate very large fully annotated synthetic image data sets. Each of those Blender files was inserted into the Rendered.ai graph that you can see in the top, and certain variations in object placement were added in order to introduce some desired variation into the data set. It's important to note here that achieving only desired variation is really ideal. We did quite a bit of iteration in order to figure out what worked best within the synthetic data pipeline, and ensuring that we only add desired variation, in this case, minimal pose variation, really allows us to generate a synthetic data set that works best with the real data that's actually collected. So we generated a synthetic data set with over 1,300 images, and you can see what those look like in the bottom four images there. And so now we have our three different data sets. We have the raw data set, the standardized data set, and the synthetic data set. And each of these data sets were converted into training and test sets of images. And we did so in such a way that these training and test images all come from the same data. So the data is directly comparable in the training and test data sets to ensure that the models that we generate are also directly comparable. So we generated several object detection models with similar training workflows for each of the 4 models highlighted to the left. So these 4 models, starting with the conventional model, was a model that was trained on raw image data applied to raw image data. The next was a model trained on synthetic image data only applied to standardized image data. And then we used Eigen's typical approach, which is standardized image data applied to, or a model trained on standardized image data applied to standardized image data. And lastly, augmenting that with synthetic data. So that gave us 4 different models that we investigated the performance of. And so here's the performance results. So the performance results that we present here are the typical COCO performance metrics for object detection. The values under the different data sets, higher values signified better performance in terms of detecting the defects and bounding them. And one thing is very clear out of these results. It is that the conventional approach of training a model on raw data only actually performs the worst out of all of the models that we developed. So adding synthetic data and leveraging standardized data are very valuable approaches to improving model performance and robustness. So Eigen's typical approach of standardized data generates improvements of nearly 200%. And then adding synthetic data on top of that to augment standardized data gives us an additional performance improvement of about an additional 21% on top of that, which shows that synthetic data is really a valuable tool to get additional performance and robustness improvements on these models. So just to summarize, so that the key findings out of the investigation is that really the conventional approach that companies have used, machine learning companies have used for years of training models on raw data is really becoming outdated. Combining standardized images with synthetic images are ways to significantly improve the performance of these models. And so synthetic or standardized images, the main benefit is that we can produce highly scalable machine learning models that are really relevant for what we do within the manufacturing industry in order to scale from one line to many. And when we augment these standardized image data sets with synthetic data, we can get significant performance improvements on top of that to generate things that we simply haven't seen yet in the factory. But it's extremely important on the synthetic data side to focus on adding desired variations into the data set and not undesired variations. The latter can actually degrade the performance. So that is a key consideration in order to get good performance out of this synthetic data augmentation. And so for anyone interested in further details about this study, feel free to access our white paper on our website, eigen.io/image twin white paper, and you'll have full details of the study and results there. So lastly, just to conclude, so it's been a pleasure to present our approach to scalable machine vision and our exploration into synthetic data. And so anyone, please, if you're interested in standardized data, standardized images, and the Eigen image twin, feel free to enroll for beta access at eigen.io. And we look forward to kind of seeing what kind of problems everyone has and can solve with our tool set. And any other questions, if you're interested in any of our other software products, you can reach out to our sales team at the link on the right. So I think that's all from my side. So back to you, Chris.
All right, Josh, that was great, and I'm happy to report that, of course, the moment I said that your voice was a little bit garbled, it completely cleared up. So all the rest of it was fantastic. It's just super exciting for me to see the both the rigor and the case study that you showed, and you really validate a lot of what we hear from customers, including things like don't introduce variation that doesn't actually occur in real data sets because it's going to degrade the performance of your models, which makes sense. But I think a lot of data scientists aren't asked to step back and think about the actual physical scenarios that they are where data is being captured. So what you described is a really great case study, learning example for customers broadly in computer vision, not just in manufacturing. All right, so we're almost at the end here. To follow up with us as well, if you happen to be at the CVPR conference next week in Vancouver, we will have a booth. We'll have a tutorial there on synthetic data and using a platform for synthetic data. We'd love to see folks there. You can sign up to try out Rendered.ai by visiting www.rendered.ai. And if you use either the content code boxes or the content code OV-demo, what you'll get access to is demonstration workspaces to do things like randomize boxes in a warehouse. Or if you're an NVIDIA Omniverse fan, what you'll actually get is access to some of the basic tutorials for NVIDIA Omniverse realized as cloud applications in Rendered.ai, and you will see the basic tutorials that they actually offer, upon which you can build to do all kinds of complex factory simulations, manufacturing simulations, and much more. And of course, synthetic data and computer vision can definitely be daunting for some folks, and we always recommend that you actually reach out to us if you want to have a conversation or a demonstration of our capabilities. And you can do that by emailing us at sales@rendered.ai. Okay, so I can't see the chat interface here, and so Stacy, who's helping us out, maybe Josh, if you can see if there are questions, maybe you can read them out and we can respond to them. And if not, I have a question for you. Let's say either you're on mute or there aren't any questions. So
there are no questions, Chris.
Okay, great, no problem. All right, so Josh, I wanted to hear from you. So when you first started working with us, one thing that you anticipated was that working with synthetic data was going to speed your time to market, because you had this idea that you could create synthetic data to train models and deploy them in production right away without even seeing real data. Can you talk to me a little bit about why that didn't work in your particular case, and what you think the nuances for somebody in manufacturing who's trying to do things like tune models to do better defect detection?
Yeah, it's a great question, Chris, and it's one of the aspects of synthetic data that we did investigate throughout this study. So the main challenge we had was that in order to get good performance out of synthetic data, it needs to be as comparable as possible to the raw data, the data that is captured by the system. If there's any differences there, then the model becomes biased towards the differences that it sees in synthetic data. So we had actually done a pretty large-scale investigation into, can we only use synthetic data combined with raw data and get good performance on completely novel situations? And the answer was no. It's very difficult to get comparable results. And so for us, the image standardization tool is a strategy also to make data more comparable to synthetic data, because it is a rendering approach, right? We are generating a 3D asset, and when we render that and generate our standardized image, it means that the synthetic data that we could generate can be much more comparable to the standardized image than the raw image, which is why we get much better performance when we generated a model on synthetic data and applied that to standardized images that it had never seen. In that case, the data was more comparable and the performance was actually better. That is to say, if it can be made more comparable to raw data, you may get similar results, but it's much more difficult because of all the other variations in the environment.
Yeah, that really makes sense. We tend to see two types of customers. One type may simply be looking for kind of what I call warm hits, where they don't have a lot of the real data. They just want to see if they can get any level of detection performance. And for those customers, what we often do see is that raw and pure synthetic data can work, and in some cases can work pretty well to achieve those raw hits or warm hits. But then what we also see in the sides of the market where you kind of are tuning computer vision algorithm performance is exactly what you described, which is one of the reasons why we emphasize physically accurate synthetic data. In these cases, you described it very well. If the synthetic data is too different at a pixel level from real data, raw data, then you'll end up tuning the algorithms to detect synthetic data, not actually to detect the variations that you want to find. For those purposes, for example, we actually allow customers to deploy another technique, which is to post-process synthetic images with a cycle GAN trained on real imagery, which kind of forces the embedding space of the parameters for the machine learning model that ends up trained on the data set to overlap better with the space of a real data set. And so what we see that in that case is better performance in terms of training on synthetic and then applying detecting to real data sets. There's lots more that we could go into there. Are there any common questions that you run into, Josh, that you wanted to cover before we close out?
I guess my main question would be, we explored a few different options to add desired variations within the Rendered.ai toolset. Are there other types of techniques, maybe generative techniques, anything that we could use in order to introduce additional novel variations that could further improve results?
Yeah, that's a great question. And the generative AI piece is something that I'm getting asked a lot about at conferences, for example. Absolutely. One area that we've already done some experimentation in is to start to use generative AI to allow a user to do a text prompt to get a greater variability in textures that are applied to a 3D CAD model, such as what you described. And so, for example, we've seen some cases where we could use that type of technique to change camouflage on military equipment in simulated remote sensing imagery. We could certainly use it to apply dirt and other things. I think there's a whole lot of research there to be done yet, because one thing I just saw an article on is that training AI on generative AI developed data can actually lead to some feedback loops that lead you down this path of then being able to mostly detect synthetic data. But I certainly think generative AI, nobody was talking about it a year ago. It is now all over the place, and it's an area that I think we're going to see a lot more application of in markets like manufacturing and many others. Any place where there's computer vision down the road. So Okay, well, I think we're right about at 45 minutes here. We don't want to keep everybody for too long. Would like to thank everyone who attended today. We will provide after the webinar and a note with the link to the presentation, the link to the white paper that Josh shared, and then we will also provide some information on how to get in touch with us. So again, thank you everyone for participating in the webinar today, and have a good rest of your day. Thanks, Josh.
Yeah, thanks a lot, everyone.